So this is just a video on the progress of the motion sleeve, which is a range of motion monitor to be used by nurses on bedridden patients in a hospital setting. As hospital volunteers, we are tasked with documenting and encouraging patients' range of motion activity. After doing some research on the susceptibility of bedridden patients to complications of immobilization, it was clear that this was a serious issue that needed to be addressed. If you're interested in learning more about this problem, I posted some articles and sites in the description. So before demonstrating the LFP in its entirety, I'm just going to go through the inner workings of it, just laid out on some prototyping boards. The messy wires make it look like there's a lot going on, but there's really not. It's just two accelerometer modules. The ADXL345 is what I went with, on one I2C bus operating at 100 kilohertz with 2K pull-up resistors. And then those are slaves to this STM32F446RE. And everything on these two breadboards, as well as the microcontroller, will be placed on the wearable, which will be worn either on the patient's leg or their arm. And then separately, we have this interfacing system here, which has a 16:2 display, and it gets its information from this Bluetooth module, which is in communication with this one at half duplex via UART. So it's a baud rate of 115/200. And this is powered by a separate AT-Mega microcontroller, which is off the screen right now. So the motion sleeve is going to be placed on the patient's leg or arm. So that means the elbow joint or the knee joint is going to be in between these two accelerometers. So the relative angle between them in one axis is what's going to be used to compute this lower angle up here. And since the hip joint as well as the shoulder joint are ball and socket joints, they have 3 axes of rotation, so that's what's going to be used to compute the pitch, yaw, and roll, which are all going to be angles relative to a calibrated position from this upper accelerometer here. So you may have noticed this RT up here at the corner, which is just the mode of the display. So right now I have it in real time. The other mode I have implemented is history, which just outputs the maximum absolute value of the angle observed for each of the axes. So you can toggle between the modes by clicking this button over here, and we can go right back. So last thing to show you guys is the alarm system here, which is just an LED in series with a piezo buzzer at 3000 hertz PWM. So if there's a mobilization for longer than a certain threshold of time, then the alarm system will go off, which is periodic. So I'm going to show you that. I'm going to wait for 4 minutes and it should go off. So I'm going to go ahead and move the lower accelerometer. So the lower angle is the only thing that should be changing. And bring it back down. And we can also do the same with the upper accelerometer as well. So now you have all 3 changing, just depending on the roll, yaw, and pitch. So this is the motion sleeve in action in real time. Now, of course, the final design will be much more comfortable as well as adjustable to fit the needs of a variety of users, as well as both the arm and leg. Donning and doffing it should also be a seamless process. The frame would be comparable to that of a physiotherapy brace, with a flexible PCB inside for all the components. Now, I mentioned the upper accelerometer is to be calibrated before using it. To do so, the user must quadruple tap it, which creates an external interrupt. The inactivity period is also an interrupt generated by the accelerometer. These interrupts help to alleviate the load from the core processor. This, in addition to its high resolution, onboard FIFO buffer, and low power mode, is what sold me. As this is an LFP, there are many improvements I want to implement in my next iteration of the design. As this is expected to be worn by many elderly patients in a hospital setting, the overall design has to be lighter and smaller. Another thing to consider is power consumption. This device will be used for long periods of time, so power must be preserved as much as possible. One way to do so is with an ultra-low power MCU. This is an STM32L151. It uses much less voltage and a lower clock source. This, however, might mean a trade-off in accuracy and speed. Another decision to make is whether to use a rechargeable battery or a power source of these several smaller ones with 3.3 voltage. This will be in series with a step-down voltage regulator, as shown in my schematic. I'd also like to improve on how the medical practitioner interfaces with the design. Something like a touchscreen LCD would open the door to more informative ways of output, something like plots or even graphical representation of the angle. The medical practitioner could even input some sort of goal system of what the patient should achieve for the day. Thank you for watching, and again, this was a learning experience for me, so if you have any feedback or just like to add on to something, don't be afraid to comment or contact me at the email I'm providing in the description. I'll also post the source code as well as the schematic in there as well. So I'll see you later for the HFP.